All right. Good morning, everyone. Sorry about the technical difficulties. I'm Amir Zamir, presenting Taskonomy, Disentangling Task Transfer Learning. And this joint work with Alexander Sachs, William Shen, Leo Guibas, Jitendra Malik, and Silvio Savarese. So let me start by asking a question. Are the problems we solve in computer vision related to each other or independent? For instance, take depth estimation and surface normal estimation, or object detection and room layout. We know the answer to the question I asked is yes, either through intuition or analytical knowledge. Like we know, surface normals are derivative of depth, or room layout provides a strong spatial priors for object detection. So some relationship between tasks clearly exists, but why does this matter, and how could such relationships be crucially useful? And that's what I'm going to talk about today. I'll show task relationships exist. They can be computationally measured without needing to encode any human knowledge in them. We see tasks as belonging to a structured space rather than isolated concepts, and this can provide us with a unified model for transfer learning. All right, so the example I showed was just for a couple of tasks, but there exist many more. And the same question can be asked about any sets of tasks, if or how they would be related. If we can answer these questions, it gives us a rather global window to relationships and redundancies between tasks. That enables us to see tasks in concert rather than in isolation, and utilize the redundancies and relationships between them to be more efficient by recycling what can be recycled. It's particularly desirable to be more efficient in terms of supervision, as we would like to solve problems with using less labeled data. And that's our focus here. Reducing the need to label data has been the intention of a large body of research literature. Self-supervised learning or unsupervised learning, meta-learning, domain adaptation, or using ImageNet features off the shelf, which is the common practice today, or the fine-tuning mechanism that we all employ. So in fact, the relationship between tasks is what enables transfer learning. So in high level, transfer learning states a model developed for one particular task may be useful for solving another if the two tasks are related in some form. Let me make that more tangible with an example. So take the problem of surface normal estimation. For this example image, this is the ground truth surface normals, and these are the surface normals results estimated by a neural network specifically trained for the task of normal estimation with a lot of data. So the results look good, obviously. And this is the results estimated by a neural network trained with 50 times less data, which gives poor results as expected. Now, here I show the results of transferring from two networks trained for two other tasks of image reshading and segmentation. The transfer is done using a small readout network trained with that 50 times less data that I mentioned earlier. So you can see that, for instance, the reshading does provide good surface normal results, right? And while segmentation doesn't do that. This suggests the relationship between reshading and surface normals is stronger than the one between segmentation and surface normals. This makes intuitive sense, since we know shading of a scene has a lot to do with the normals of the surfaces in it, while relationship between segmentation and normals is not clear to be existing. So we observed when problems appear related, they could supply useful information for solving each other. And if we have some machinery for quantifying such relationships at a scale between any sets of tasks, we can form that complete graph that gives us the global window that we wanted to have to understand the redundancies between tasks. For instance, this can be used to solve a set of tasks in concert while minimizing the required supervision by leveraging the redundancies that I mentioned earlier, as shown here, where all tasks are being transferred to from only 3 sources. Or solve a desired novel task, which we don't have enough labeled data for. That's because solving a new task becomes a matter of inserting it in this structure rather than starting from scratch. So this is what taxonomy is about. It's a fully computational method for quantifying task relationships at a scale and extracting a unified structure out of them as a model for transfer learning. We call it task taxonomy or taskonomy, as it devises a taxonomical transfer policy over tasks. Okay, so here's more details about how we do this. First, we define a set of tasks, including a broad set of 26 semantic 3D and 2D problems. This dictionary is not meant to be an exhaustive list of all vision tasks that we care about, but it's a sample set that we use actually for modeling. We'll discuss generalization out of this dictionary later in the talk. We collected a set of about 4 million images of indoor scenes where each image has ground truth annotations for each of the 26 tasks. These images are real, they are not synthetic, and they are registered against 3D meshes that are actually reconstructed using a structured light sensors. So that makes the process of extracting the ground truth of our 3D tasks easier for us. All right, then we train a network for each of the 26 tasks that we have in our dictionary. We call them task-specific networks. So here you can see the results of these networks applied frame by frame on a YouTube video. Here, this bounding box shows a subset of 3D tasks, for instance, 3D curvature, or here are the semantic tasks, like object detection, and some self-supervised tasks, like colorization, and some low-level tasks, like edges and key points. All right, so our modeling has 4 main steps. As I mentioned earlier, in the first step, we train a task-specific network for each of the tasks that we have in our dictionary. And we freeze their weights. We freeze their weights. Now we repeat the process for all of the tasks that we have in our dictionary. So each task at this point will have one task-specific network. Now the next step is quantifying the relationship between tasks. Like for instance, take the relationship between normals and curvature. We take the encoder of the task-specific network of normals with the frozen weights, and we train a small readout network to read curvature from the representation of the normal encoder. This small network is then evaluated on an unseen test set, and its performance determines the edge weight, specifying the strength of their directed transfer relationship. All right. Well, as there are 26 tasks in our dictionary, there are 26 by 25 feasible transfer functions, and we train all of them. So at this point, this gives us the complete directed graph of relationships that we wanted. However, these values require normalization, as these tasks live in different output spaces and with different numerical properties. This is best visible over the adjacency matrix of the complete graph that I'm showing up there, where you can see that certain rows are clearly dominating the matrix. That's because of the fact that I mentioned that these tasks are living in different output spaces. So we need to normalize this. So we normalize this matrix using an ordinal scheme called analytic hierarchical process. I'm not going to get into too much details about that, but briefly we adopted an ordinal scheme since it makes less assumptions about the numerical properties of the output spaces compared to linear normalization or similar parametric approaches, and we found that to be crucial. We have more details of this in the paper and the poster. All right, so at this point, we have our affinity matrix, the complete graph of relationships completely normalized. So this complete graph of relationships is essentially exhaustively quantified, pairwise set of tasks evaluated in terms of transfer dependency. Notice that all of these transfers are not useful. Many of them are weak, but there are quite a strong ones there too, and clearly exist some patterns. So we would like to extract a sparse structure out of them, out of this complete graph. This sparse structure should maximize the performance of solving all tasks and tell us what tasks are better to be picked as source to best support solving all other tasks, or how to transfer to a novel task that we hadn't in our original task dictionary, right? So again, without getting into details in the talk, in interest of time, about this particular step, this problem can be formulated as a subgraph selection. Well, we define a dictionary here, which includes both previously seen tasks, shown by gray notes here, as well as novel tasks shown by red notes here. Then we code a set of constraints and optimize them using binary integer programming to extract the optimal subgraph. Now, the details of this step are again in the paper and poster, but it's straightforward. So at this point, to summarize, the output of the subgraph selection process devises a connectivity that solves all targets, including the novel ones, maximizes their collective performance while using only the available sources, and no more than a user-specified budget, which determines the maximum allowed number of used source tasks. And that's what we wanted, and that's our taxonomy. So one point that I skipped in interest of time was also higher order transfers. Higher order transfers are the cases where two or more source tasks get together to transfer to a budget, and we include them in our framework. So our affinity matrix is actually much bigger than 26 by 25 because it includes the higher order case as well. All right, so some experimental results. Like I said, we have 26 total number of tasks, therefore 26 task-specific networks, about 3,000 transfer functions, which took about 47,000 GPU hours to train. Good for cloud computing companies. The transfer functions were trained with 8 to 100 times less training data than task-specific networks. All right, so here's a sample taxonomy. This particular taxonomy was computed to solve the 26 tasks that I put down there. With 4 of them are target-only tasks, meaning that they had only very limited data, supervised data, that was just enough to train the readout functions, but obviously not the full task-specific networks. So look at the connectivity. Intuitively makes sense. 3D tasks are usually connected to other 3D tasks, or similarly, semantic tasks. They're getting their information from other semantic tasks and optionally maybe higher order information from other neighboring tasks. So to quantify the results that this transfer policy would achieve, we use 2 metrics, gain and quality. The color coding here shows the value of gain. Gain is a win rate that quantifies how much value was gained by employing transferring. So note that gain values are usually deep blue, denoting 100%, meaning that there was a lot of benefit in using transfer learning and not. Here I'm showing the quality values. The quality metric is a win rate that quantifies how close to gold standard task-specific networks the transfer results got. So again, note that the quality values often approach white, which denote 50%, meaning that certain transfer results started getting close to their gold standard task-specific networks. All right, so this was just sample taxonomy. Taxonomy can be computed with arbitrary arguments, and the best way to understand it is through our live web API, which you can specify any argument you want, run Taskonomy, and see the qualitative and quantitative results. Specifically, the results compared to using ImageNet features, which is the popular practice again today, that you can see there that ImageNet features are outperformed significantly by using taxonomical features, which has actually important implications that we have discussed in the paper. We also have a set of experiments in the paper. They're important, but we didn't include them in the talk. For instance, significance test, showing how important it is to use this particular taxonomy found by our method rather than just any connectivity. Evaluating the trends found on taxonomy dataset on ImageNet and MIT places to make sure the results are not dataset specific. We evaluate the sensitivity to choice of dictionary. We evaluate model dependence by testing on varying architectures, and also generalization to single out-of-network tasks, and compare that to self-supervised and unsupervised ImageNet-based baselines that again show they are outperformed by a large margin, and the implications of that are discussed in the paper again. So to summary, we took a striving first step towards understanding the space of vision tasks. And we started treating tasks in concert, coming from a rather structured space, as opposed to isolated concepts, as illustrated in this force atlas plot that was created using our quantified relationships. We proposed a fully computational framework for this purpose, providing a unified model for transfer learning, and we are moving hopefully towards a generalist model for perception. And generalist model for perception. And I can take questions while I play YouTube video of actually the convention center that we applied the task bank on. You can see the results here. We also thank the award committee for the recognition.
So again, if you have questions, please come up to the microphones.
Yes, this is excellent work. Say I have a new task that's not one of your 26 tasks, and I want to apply what you've learned. How do I know which of your 26 pre-trained networks to use towards my new task?
Right. Yeah, so that's specifically included in the formulation. So if you remember the plot that I showed, there was like some red task and some gray. The red tasks are those, the ones that you haven't seen before, but now you want to solve them. And that's the process of essentially insertion. So So for those, you need a very limited amount of data, let's say 2,000 images, to be able to train those readout functions. So that essentially tells you where in that like circular graph your new task belongs, right? Obviously, you can't use your new task as a source because you can't train a fully fleshed network for it. But that process is just enough for it to tell you which sources are best supporting that particular task. And for instance, the taxonomy that I showed, 4 of the tasks were like fitting the scenario that you explained. There was no supervised data for it except for like 2,000 images.
Thank you.
No worries.
How does your task graph help us in understanding joint training tasks? So if you wanted to train, say, a dense task like segmentation and a discriminative task like classification to have one joint network, what does this task graph tell us about training processes that are like that? They
Right.
seem kind of complementary.
Right. So essentially, you're pointing out like multitask learning.
Right.
You want to actually have one network completely blended together to provide 2 outputs. In a way, it's actually the opposite of what we do.
Right.
We keep them separate and just merge them in the end. The question that you're asking doesn't have a clear answer based on like what we have studied here. But I can tell you that basically, again, the relationships obviously here will tell you the similarities and let's say in a sense of mutual information between tasks. So I would definitely expect that to be a guideline for which tasks to be merged into one network.
Right.
Let's say how much you would need to expand your learning capacity when you add one more task. Obviously, if 2 tasks are similar, I would expect not much learning capacity needs to be added to our network and so on. So I think basically the answer to your questions, the guideline would be in those like quantified relationships.
Right.
Yeah.
Okay. Thank you.
All right, I think we're out of time, so let's thank Amir again.